Hey guys, welcome back to part 3 of simple harmonic motion. Uh, Today I'll derive the equation for the period of a mass spring system. So our total energy is 1 half kx squared. Our x is a special x, which is A, which is the amplitude. And so I can say that at any point, this total energy is equal to whatever's made up of the potential energy and whatever's made up of the kinetic energy. And your book moves this around so that they can solve for what V is and what V max is. All right, so an ideal spring has a spring constant of 670 newtons per meter. It's compressed 0.9 meters. What is its potential energy? If a 2 kilogram mass is placed against a spring and is released, how fast will the mass be moving? So we did this problem previously, but just to get back with our using conservation of energy. So energy would be 1 half kx squared. And so this is 670. And our amplitude, our maximum x is 0.9. If I put this in my calculator, I get 271 joules. If there are no non-conservative forces, I can find out what my maximum speed would be by setting this equal to the formula for kinetic energy. So if you were to release this, we could get all of the energy as energy of motion, and I could solve for V by taking 2 times 271 divided by m, which we're saying is 2, and square root. And so I have 16.5 meters per second for that one. All right, so they're going to try to use something moving in a circle to derive the simple harmonic motion formula. I'm going to do it a little bit differently. All right, so this is our formula. The T is equal to 2 pi square root of m over k. I'm going to start with the relationship that we have with the mass spring system. And what we would say is that we have that F of S is equal to negative kx. Now, although you can't use kinematics for this, I can use Newton's second law. And so I would say that F net is equal to ma. And so what I'm left with is that ma is equal to negative kx. So what is x? X is our position, and we defined x as a cosine omega t, where omega, our angular frequency, is 2 pi over t. So what's our relationship between acceleration and position? It turns out that acceleration is the second derivative of position with respect to time. So I'm going to take the first derivative of this, and we can call this either x dot or dx dt, and this would be equal to negative a omega sine of omega t. And then I would take the second derivative with respect to time, and this is going to be negative a omega squared cosine omega t. And I'll explain to you guys why the derivative of cosine is negative sine and sine is cosine. All right, so now I'm going to plug in this for acceleration, and I'm going to plug in that for position. I'm going to move this around a little bit, and we know that we can multiply things in any order, so I'm going to write our x double prime, which is our acceleration, as equal to minus omega squared a cosine omega t. And so over here I have m times negative omega squared a cosine omega t equals negative k a cosine omega t. So when I move that around, I got a cosine omega t by itself. So I can cancel that out. So that term and that term go away, and so does the negative. So what I'm left with, if I take the mass to the other side, is that omega squared equals m over k. Well, I know that omega is 2 pi over t. Oh, I messed that up. It's k over m, not m over k, right? So I divided both sides by m. All right, so I am going to express this out and get the t squared to the side by itself. So I'm going to have 4 pi squared equals t squared k over m. And then I'm going to multiply by mass and divide by the spring force constant, and I get t squared equals 4 pi squared m over k, and then I'm going to square root both sides, and I'm going to get that t is 2 pi m over k. So how long this period takes is a function of the mass and the spring force constant. If you remember that previous multiple choice problem, they said if you added a mass to the end of the spring, how would it change the period or the energy? And I said the energy wouldn't change because at that point, all of the energy was spring energy. The period would get bigger because you made the top of the fraction bigger. So this is our formula. This is on your equation sheet. And I like to put a little subscript s on there. And then again, we know that frequency is 1 over t, so it can be written as this way too. But this is the way that we write it. And I think that this derivation is the more common one. I'm not sure what the book's trying to show with that. Okay, so what is the period of a mass spring system if it is stretched 2 meters and it has a mass of 5 kilograms and a spring constant of 20 newtons per meter? So our formula is that T of S is equal to 2 pi m over k. So it is 5 kilograms over 20 newtons per meter. which this is 1 over 4 square root would be 1/2. 1/2 times 2 would be 1. So our period is pi seconds. Notice that the displacement doesn't matter. And again, as I've said, they like to focus on things that go against common sense. And it doesn't make a lot of sense that it doesn't matter how much you displace a mass spring system, it has exactly the same period. But that is the case, and you guys will see that in labs as well. All right, so here's our position. And I use this for the derivation that it's A cosine omega t. You can also write this as A cosine 2 pi f. And again, this is our angular frequency, which is 2 pi times the frequency, or 2 pi over the period. A is our amplitude. And so any of these are acceptable and they're exactly the same. It's convenient just to use omega because it's, one single letter as opposed to the 3 terms for that one. All right, so a particle moves in a circle in such a way the x and y coordinates of its motion are given in meters as a function of time, in seconds by x equals 5 cosine 3t, y equals 5 cosine 3t. What's the period of revolution of the particle? So they're telling us that our angular frequency is 3. That's what I'm getting out of this. I can make this bigger. Maybe I can. I also know that omega is 2 pi over t. So t would be equal to 2 pi over omega, which would be 2 pi over 3. So it is 2/3 pi. So this is a convenient thing to find out just looking at one of these functions, what the period's going to be. An object at the end of a spring with the spring constant k moves in simple harmonic motion with an amplitude a and a frequency f. Which of the following is a possible expression for the kinetic energy of the object as a function of time? Okay, so kinetic energy is 1/2 mv squared. We're saying that x is a cosine omega t. So v is the derivative of this, right? So v would be equal to dx dt. And this would be negative a omega sine omega t. It would also be equal to one half k a squared right? This is going to be 1. cosine of 0 is 1, so cosine of all right, now I'm just going to enter a spring with the spring constant K moves in simple harmonic motion with amplitude A and frequency F, which the following is a possible expression for the kinetic energy as a function of time. Kinetic energy is going to be equal to our potential energy. Our potential energy is 1/2 Ka squared at T equals 0. Cosine squared of 0 is 1, and so we get 1/2 Ka squared. So B is our choice. A 2 kilogram mass connected to a spring oscillates on a horizontal frictionless surface with a simple harmonic motion of amplitude of 0.4 meters. The spring constant is 50 newtons per meter. The period of this motion is. So I have 2 pi times 2 over 50. So that would be 1 over 25, or the square root of 1 over 25 would be 1 over 5. So I have 2/5 pi, which is 0.4. The maximum velocity occurs when the spring is neither stretched nor compressed, so the displacement from equilibrium is equal to 0. Two blocks are connected to ideal springs and are oscillating on a horizontal frictionless surface. Block A has a mass of m, and its motion is represented by the graph of position as a function of time as shown above on the left. Block B's motion is represented above on the right. Which the following statements comparing block B to block A is correct. Because block B covers more distance per cycle than block B takes more time to complete each cycle. The period is 2 seconds for block A. The period for one cycle for that one is 4 seconds. Because the spring attached to block B is initially stretched a greater distance, the spring constant is smaller, and therefore block B has a slower average speed than block A does. Because block B has more mass, it has a slower average speed than block A does. Because block B has more mass, its acceleration is smaller than block A at any given displacement. Okay, so if they're identical ideal springs, K is the same. It is not a spring constant would be determined by what makes equilibrium. It is D. Because block B has more mass, its acceleration is smaller than that of block A at any given displacement. So I can't say it's C because its average speed is going to be related to not just the mass, but also to how far you displace it, right? Because they have the same K. But I do know that the Ks are the same. And if M is bigger for B, then A is going to have to be smaller, right? Because it has this inverse relationship for any given X. So D is our best answer.